Today we're going to do a review of how exponential and logarithmic functions work. And so we'll start off with the exponential functions. And you'll remember from pre-calc that those are functions such as f of x equals a to the x. And the big thing that makes it an exponential is that the variable is in the exponent. Now there's lots of applications of these functions. First, though, we're going to work with them, and then we'll talk about some applications, and then in tomorrow's video, actually, we're going to go into a few more applications. So first, what does the graph of an exponential function look like? Graph of an exponential function is going to look something like this, where it comes in shallow, and as soon as it breaks into the positive, it's going to go up significantly fast. And so if this is the graph of f of x equals a to the x, there's two key points and then a key asymptote that we're going to be interested in. The first key point is when x is equal to 0. We end up with a to the 0 power, and anything to the 0 is 1. The second key point is over here at 1, comma, and a to the first power is just a. So whatever the base is going to be the height of that. There's also going to be a horizontal asymptote at y equals 0, and that's what the graph is going to get close to on the left side. It levels out, never actually getting to 0. So if this is the parent function, let's see if we can use what we learned about graphs to make the adjustment, or the shifts, to end up with f of x equals 2 to the x plus 1 minus 3. Now if we start with our graph, the basic graph before it shifts and moves around is going to look like this. It's got a key point at 0, 1, and a key point here at 1, the base in this case is 2. But then what we'll see is we have a, let me change the color here, we have a plus 1 in with the x. That's going to move the graph left 1 unit. We also have a minus 3. That's going to move the graph down 3 units. So if we move left 1 down 3, I need to drop my graph a bit. So there's 1, 2, 1, 2, 3, 1, 2, 3, 1, 2, 3. If we take the 0, 0 and move it left 1 down 3, it ends up right here. And if we take the 1, 2, move it left 1 down 3, it ends up over here. And then, of course, the asymptote moves down 3 as well. And so we end up with this graph, which is the graph of 2 to the x plus 1 minus 3. So the pink graph is actually my solution. The blue graph is the original graph. So all those same translations apply to graphs of exponentials. However, what we're really interested in, what was that, number 2? So this is number 3. What we're really interested in is solving equations. And with exponentials, the key thing with equations that we need to know is if we have the same base, a to the x equals a to the y, if we have the same base, then we say that x equals y. If the bases are the same, the exponents are the same. You might remember we did that by taking a log base a of both sides, and the exponent came out. We'll talk about that more when we get to logs, though. For now, let's take a look at a couple examples. Let's say I have 2 to the 3x equals 2 to the 7th. Because we've got the same base, what we can do is we can say, well, then these exponents must also be the same. So 3x equals 7, and divide by 3, and x is equal to 7/3. That was probably too easy, though. Let's try one that's a little more involved. How about 25 to the x equals 1 over 125? These sides both have different bases, and so they're not going to work as nicely unless we can get them to have the same base. And you'll recall that 25 is 5 squared to the x. Equals 125 is 5 cubed, and the way we make a fraction is if the exponent is negative. So now we've got the same base of 5. We've got 2x and negative 3. That must be equal. 2x equals negative 3. Divide both sides by 2, and x is negative 3/2. Let's try one more that's a little more involved than that. How about we try 16 to the 2x plus 3 equals 32 to the 5x plus 3. Here, we'll want to write each of these with a common base, and you might notice that common base is 2. 16 is 2 to the 4th to the 2x plus 3 equals 32 is 2 to the 5th to the 5x plus 3. Now I want to notice the 4 and the 5 exponents are not just multiplied by the first term, they're multiplied by the entire exponent. So when we set them equal, we'll have the 4 is going to multiply by the 2x plus 3, and the 5 is going to multiply by the 5x minus 3. This gives us 4 times 2x plus 3 equals 5 times 5x minus 3. And we should be able to solve this quite nicely. Distribute to get 8x plus 12 equals 25x minus 15. Subtract 8x from both sides. That's going to give us 17x on the right. Add 15 to both sides. That's going to give us 27 on the left. Divide by 17, and x is equal to 27 over 17. So that's how we can solve basic exponential equations. Now, one application of these exponential equations that we're going to get more in detail with tomorrow's video is this idea of compound interest. And you might remember this compound interest formula from some of your previous math classes, or maybe even some of your business classes. A equals P times 1 plus R over N to the NT power. So if I were to invest $3,000 at 8% compounded quarterly for 5 years, that means interest is paid into my account every quarter, 1/4 of the 8% for 5 years. So A, my accumulated final future value, is equal to the principal present value of the money, $3,000, times 1 plus the interest rate of 0.08, divided by n, which is the number of compounds in a year. It's compounded quarterly of 4, to the 4 times t. T is 5. And then we just need to plug this into our calculators. To plug it into our calculator, we'll type it just like it looks, with one minor exception. We've got 3,000 parentheses 1 plus 0.08 divided by 4, close the parentheses. And when we rise to an exponent, some calculators will take you into the exponent, like the TI-84 here did, and we can say 4 times 5 up in the exponent. Some calculators will just stick a little caret that looks like the symbol right above the division sign. If that's the case, you need to put the 4 times 5 in parentheses. Make sure you know how your calculator works. Make sure you get 4,457.84. And that's how much will be in the account after 4 years. Sorry, 5 years. You might remember from some of your other classes that the more often it is compounded, the more money you're going to make at the end of a year. And it goes all the way up to this thing called continuous interest. And the idea with continuous interest is you get an infinite number of compounds. You may remember that continuous interest is A, the accumulated final value equals PERT, principal, times e to the RT power. So let's try an example with that. Let's take our same $3,000 at 8%, but this time compounded continuously for 5 years. And see what having infinite compounds is going to do to change this situation, how much more money we're going to earn. So we have A equals P, principal of $3,000, times E, that's Euler's constant E, the 2.718, to the R, which is 0.08, times T, which is 5 years. Again, we'll do that on our calculator. 3,000. To get the E, we're going to hit the second button in the top left first, and then we will hit the LN, which is right next to the number 4. That will either open up a parentheses if you have a TI-83, or it'll stick you in the exponent if you have a TI-84. Since that's already taken care of, we can just type in 0.08 times 5 and hit enter, and we have 4475.47. 4475.47. So a little bit more money, about $20 more, if it was compounded continuously. So that's your quick review of exponential functions. We're going to spend a little bit more time talking about logarithmic functions, because they're more interesting and you can do more with them. And a logarithmic function is written something like x equals log base b of a, which really means b, the base, raised to the x exponent equals some answer. The ability to convert between these two formats is what makes all the other log stuff work. So you do need to know how to convert. The big thing I remember is that the log is or equals the exponent. The log is the exponent. Whatever the log equals is the exponent. So when you're asked to write something as a log, you end up with 3 to the x equals y. To change this to a log, we see that the base of the problem is 3, same as the base of the log. We put the answer inside the log, and it's going to equal the exponent of x. How about this one? A to the 2x equals 37. You might pause the video and try and do it first on your own. This is log base a of 37 equals the exponent of 2x. Logs will always equal the exponent. And we can go the other way as well. I can give you a log and ask you to write it as an exponent. Let's say I gave you log base 2 of x equals 7. Well, the base we know is 2. Let me do it in a different color. The base is 2. The log equals the exponent of 7, so 2 to the 7th must equal x. How about this one? Log base 7 of 1 equals 0. Maybe pause the video and try it on your own. The base is 7. The exponent is 0. The answer is 1. That's really the basics of logarithms, is converting them between logs and exponents. Now, we do have some properties of logs. That are very similar to the properties of exponents, because logs really are exponents. If we have the log base a of xy, that is equal to, we could expand that to the log base a of x plus the log base a of y. And this comes from the property just using different variables, but if we had m to the p times m to the q, we would say that's m to the p plus q. That's kind of where it stems from, is when we multiply two logs together, we're going to add the exponents. So if we multiply inside a log together, we add the exponents. We add the logs. Similarly, if we have log base a of x over y, just like if we were dividing with exponents, we subtract then, we'll also subtract these logs. Log base a of x minus log base a of y. And again, that comes from m to the p over m to the q. We subtract those exponents, p minus q. And because logs are exponents, we're going to subtract the logs with a quotient. Another important property of logarithms is that the log base a of x to the r, if we have an exponent inside the logarithm, this is the one we'll use the most, it's going to come out in front of the log. R log base a of x. We multiply by that. We multiply the exponents together, essentially. Because remember, a log is an exponent. It comes from m to the p to the q. A log is an exponent, and we have another exponent. We multiply those exponents together, p times q. A couple more that just kind of come out of the definition of a logarithm. If I have log base a of a, what we're really saying is a to some power equals a. Well, clearly, a to the first power equals a. So log base a of a is going to be equal to 1. If the base and the inside match, the solution is 1. If I have log base a of 1, again, we're saying a to some exponent equals 1. Well, we know that anything to the 0 power equals 1. Maybe I could write these down, make it a little visual. Anything to the 0 power equals 1. Anything to the first power equals itself. That's what we're really saying. And this one combines a couple properties together, but it's a nice little property, log base a of a to the r. The r is going to move out front. Log base a of a is 1, and so we end up with just r. Which makes sense, because if we wrote this as an exponent, we would have a to the r equals a to the r. And I think we would all agree that that is true. So over here in blue on the right side, that's where the properties come from. What I want you to know is be able to use them, the ones in black. So let's try and use the properties of logs. So we might see a problem like the log base a of x plus the log base a of 3y. We could combine these all into a single log base a. When logs are added, we have a property that says added logs becomes a log of the product. So we will multiply those together. X times 3y is 3xy, and we've combined those into a single log. We can go the other way. We can go from a single log, like log base a of x squared minus 3x over x plus 2. Now, one thing I want to notice is that numerator can be factored. That numerator has a common factor in it. So what we really have is log base a of x times x minus 3 over x plus 2. And so we can expand this out and have one log for each factor, a factor that is multiplied or divided. So in the numerator, we've got a log base a of x. It's multiplied, so we add log base a of x minus 3. Then we divide. Division of exponents turns into subtraction. Log log base a of x plus 2. This is going to be my expanded final answer. I want to note, very important, we did not distribute the log through parentheses. We cannot distribute logs through parentheses. It does not work. Do not distribute logs through parentheses. There's no such property. It doesn't work. That's like distributing square root. That just doesn't make sense. Log is an operation. You cannot distribute log through parentheses. However, we can split up factors with adding and subtracting them. How about this one? Log base a of 3x to the 5th a squared over 2b cubed. Well, if we start expanding one log for every factor, we have log base a of 3 plus, because it's multiplied, log base a of x to the 5th plus, because it's multiplied, log base a of a squared minus, because we're dividing by it, log base a of 2. And then I want to notice, again, we're going to subtract log base a of b cubed. Notice that the negative logs were from the bottom. That is because a negative exponent moves something to the bottom of a fraction. Everything from the bottom of a fraction has a negative exponent, comes from a negative log. However, we can do a little bit more simplifying. You might notice we've got some exponents that can move out front of these logs. You also might notice that we've got a property of log base a of a squared. Because the base of the log and the base of the exponent match, the solution there is just the exponent. So we end up with log base a of 3 plus 5, moving the exponent out front, log base a of x, plus 2, bases match, so the answer is the exponent, minus log base a of 2 minus 3 log base a of b. This is our final expanded solution. Now, a common question that comes out of this is why on earth would we want to be interested in expanding logs and contracting logs? What is the advantage? Well, back in the day, probably before most of you were born, we didn't have these fancy calculators that can do all this work for us. And so what we had is we had log tables. And in a log table, you would look up a given base and you would find what all the logs were equal to of the prime numbers. For example, we'd be told that log of some base of 3 is equal to 2.1. And we'd see the next prime number of 5. Log base A of 5 would be equal to 2.7. And then we would have to use these properties in order to find out what various logs were equal to. For example, if we want to know what log base A of 9 was, well, 9 is 3 squared. Log base A of 3 squared. And our exponent property says we can move the exponent of 2 out front. So we have 2 log base A of 3. And our table tells us what the log of 3 is. The log of 3 is 2.1. So 2 times 2.1 is 4.2. And we've got our final solution. The log of 9 then must be 4.2. How about this one? The log base A of 15. Well, we would know that 15, if we factored it, because it's always about factors, 15 is 3 times 5. Whoops. Lost my numbers. There we go. So we could expand this because we're multiplying. We add the logs together. Log base A of 3 plus log base A of 5. And then we can use that substitution that we're given. Log of 3 is 2.1 plus the log of 5 is 2.7. So log 15 must be equal to 4.8. Now, we don't really use tables anymore, which is a sad loss for all things mathematical and requiring thought. It's okay, I'll get over it. Number 6, now we can do logs on the calculator. We just need to employ a slightly different strategy now, though. There are 2 log buttons on your calculator. One of them is a base 10. It is the unwritten log, if you will. If you see log base 10 of 7, you probably never would see log base 10 of 7. Because instead, we just write log 7. There's no 10 written. If there is no base written, we will always assume that means a base 10, which is the same as the log button right next to the number 7 on your calculator. So if I push the log button next to 7, hit the 7, and enter, I see that log of 7 is 0.845. So that's the unwritten base 10. The other base that your calculator can do is a base of e. That's Euler's constant. It is written as ln. Stands for natural log. I know the letters are backwards. It's because it comes from the Italian or the Latin, not English, which is weird, where the nouns and the verbs are all backwards. So log natural, the natural log. So if we see a problem like the log base e of 7, well, that would never be written. We would write natural log of 7. And there is a natural log button right next to the number 4, ln of 7. And you'll see if you hit enter, that's equal to 1.946 about. So those are the only 2 bases your calculator can do. So what do we do about a log base 5? How do you put that in your calculator? Well, we have this thing called the change of base formula. And the change of base formula says we can take, let me get more space. We can take log base anything of x, and we can change it to a different base. Let's say we want to do a log base b. That works now. We can stick the x in there. We just have to divide by the log base b of the old base. And we usually will use either a base 10, or in calculus, we like natural logs a lot better than base 10 logs, common logs. So we would write ln of x divided by ln of a. The natural log of x divided by the natural log of a. So, for example, if we wanted to do the log base 5 of 27, we can change it to a natural log, the natural log of the 27, divided by the natural log of the old base, and that's going to be equal to the exact same thing. And we can do this on our calculator, the natural log of 27. Very important, you close the parentheses, divided by the natural log of 5, making sure you close parentheses when logs are done, and you should end up with about 2.05. And if you did 5 to the 2.05 on your calculator, you would end up with approximately 27. So that's how we do them now on calculators with the change of base formula. We're ready now to get into the good meat of this stuff, is solving log equations and solving exponential equations. First, though, let's solve log equations, because we're talking about logs right now. We already talked about exponents, or so you thought. First, we're going to look at log base x of 1 over 64 equals 3. The general rule we're going to run into with logs and exponents is if you can't solve it in one form, switch to the other form. So in this case, we don't really know what the base is going to be, so we switch to the other form where we change it to an exponent problem. X to the third power equals 1 over 64. Well, the opposite of a third power is a third root. So that leaves us with x equals, the third root of 1 is 1, the third root of 64 is 4, so the base must be 1/4. How about this problem? Let's do the log base 9 of x equals 7/2. Again, we don't know what the x is, so let's change it to an exponent. 9 to the 7/2 equals x. Well, the half, that's like taking a square root of 9, so that's now a 3 to the 7th equals x. And I'm going to cheat and go to my calculator to do 3 to the 7th power, because it's going to be huge. 2187 is equal to x. We can use some of our properties of logarithms also to help us solve log problems. If we have a log base 3 of x minus 2 plus log base 3 of x plus 3 equals 6. We almost feel like we've run into a bit of trouble when we've got two logs in the same screen. But we can combine them to a single log because they are added. This gives us log base 3 of x minus 2 times x plus 3 equals 6. Now that it's a single log, we can rewrite it as an exponent problem. X minus 2 times x plus 3 equals 3 to the 6th power, again is large, 3 to the 6th power, 729. And then we can solve this like we did back in Algebra 2, x squared plus x minus 6 when we FOIL equals 729. Subtract 729 from both sides, and we get x squared plus x minus 735 equals 0. And then we could solve from here. Probably not going to be able to factor. It's going to be something ugly. We're going to have to use the quadratic formula. So x is equal to the opposite of b plus or minus the square root of b squared minus 4ac all over 2a. Remember, the two negatives make a positive, so we've got negative 1 plus or minus the square root of 1 squared plus 4 times 1 times 735. Oops, 735. Square root of 2941 over 2 times 1 is 2. And I don't think that radical reduces, so we'll leave it like that. That one got kind of ugly. Hopefully they'll be nicer to us on the homework assignment. How about this one? Log base 2 of 1/8. We can actually evaluate what this equals. For the sake of discussion, we'll just say it equals x, and x is always our solution to the problem. Change it to an exponent problem. 2 to the x equals 1/8. And this looks just like one of the exponent problems we saw earlier in the lesson. 2 to the x equals 2 to the, well, 8 is third power. We make it negative so that we get the fraction. And x, or the log base 2 of 1/8, is equal to negative 3. How about this one? Let's do the log base 2 of 5x plus 1 minus the log base 2 of 3x plus 6 equals the log base 2 of 7. Again, with several logs on one side of the equation, it's going to be very difficult to solve. So we'll combine them into a single log with subtraction. That means we divide the guts. 5x plus 1 divided by 3x plus 6 is going to equal the log base 2 of 7. And you may recall that we said if a to the x equals a to the y, then x equals y. If the bases match, then the exponents are equal. Notice our bases of the logs here match, so the guts must be equal. 5x plus 1 over 3x plus 6 must equal the guts of the other one, the 7. We can solve this by multiplying both sides by the LCD of 3x plus 6. I'm not sure why that made my 5x plus 1 disappear. That was interesting. The 3x plus 6's divide out, and we have 5x plus 1 equals 21x plus 42. Now we're in business. Subtract 5 from both sides to get 16x. Subtract 42 from both sides to get negative 41. Divide both sides by 16, and we get negative 41 over 16 equals x. So that's solving log equations. We can either convert them to an exponent, we can use our exponent properties to combine logs and then convert them to an exponent, Or if we've got logs on both sides, we just get it down to 1 log on each side, and then the guts must be equal to each other. Yes, guts is a very mathematical term that we'll end up using a lot when we get to our next unit on derivatives. Now that we're good at solving exponential equations, let's solve some now that we're good at solving logarithmic equations, let's solve real exponential equations. But isn't that what we did earlier? Didn't we get the same base on both sides and set the exponents equal? Wasn't that solving exponent equations? Well, yeah, but those problems were really nice. We got the same base on both sides. What do we do, leaving a line for a few more notes, but what do we do when we have 5 to the x equals 7? We can't get the same base there. So what we're going to do is we're going to take the natural log of both sides. That's going to be our strategy. If we can't get the same base, we will take the natural log of both sides. When we do that, we get the natural log of 5 to the x equals the natural log of 7. And now that all-important property says that the exponent can now move out front. X natural log of 5 is equal to the natural log of 7. Divide both sides by the natural log of 5 to get the x alone. And x is equal to the natural log of 7 divided by the natural log of 5, which our calculator can do quite nicely for us. The natural log of 7, close the parentheses, very important, divided by the natural log of 5. And the answer is 1.209. We have our solution. Now we can make these a little more interesting to us, but we still apply the same strategy. Let's say we have 6 to the 3x equals 5 to the x minus 4. Again, we can't get the same base, so we will take the natural log of both sides. So the natural log of 6 to the 3x is equal to the natural log of 5 to the x minus 4. Whoops, too far. And again, we've got exponents inside the logarithms that come out to the front. We have 3x natural log of 6 equals, and to make sure we multiply by the entire exponent, we'll put it in parentheses, x minus 4 natural log of 5. To keep solving, we're going to need to distribute through the parentheses so that we can get at those x's. We now have 3x natural log of 6 equals x natural log of 5 minus 4 natural log of 5. Let's get all the x's on one side. We'll subtract x natural log of 5 from both sides. Now be careful, those are not like terms, so we can't really do much with them. One has a natural log 6, the other has a natural log 5. You cannot add those and get 11. No, that's bad. They are not like terms. So we have 3x natural log of 6 minus, well, we couldn't subtract them either. I probably should have said subtract natural log of 1. That's bad too. Minus x natural log of 5 equals negative 4 natural log of 5. Since both of these terms on the left have an x, we can factor out that GCF of x. That leaves us with 3 natural logs of 6 minus the natural log of 5 equals negative 4 natural log of 5. And the beautiful thing is now the x is alone. We can get it isolated by dividing by that parentheses 3 natural log 6 minus natural log 5. You need to keep it in parentheses for when we get to the calculator part. So to type this in the calculator, -4 natural log of 5, close the log parentheses. Then when we divide, we need to put the entire denominator in parentheses. 3 natural log of 6, close the parentheses on the natural log, minus the natural log of 5, close the parentheses on the natural log, close the parentheses on the denominator, hit enter, and we finally have our solution, -1.71. That is our solution for x. Let's do one more. Let's do 2e to the 0.03t equals 7. Kind of hinting at what we're going to get to tomorrow. Well, before we take the log of each side, let's get the part with the exponent, the e to the 0.03t alone. And the way we get that alone is we're going to divide out that 2 from both sides. So we have e to the 0.03t is equal to 7/2. And this actually is quite nice. When we take the natural log of both sides, we end up with the natural log of e to the 0.03t equals the natural log of 7/2. But remember, the base of the natural log is e. And so when the base matches the base, the natural log of e divides out, or undoes each other, unexponents, I guess you could say. And so we have 0.03t of the natural log of 7/2. Quickly get t alone by dividing by 0.03. And t is equal to the natural log of 7/2 divided by 0.03. Our calculator can take care of that quite nicely for us. The natural log of 7/2, close the natural log, divided by 0.03, and we get 41.76. We will use tomorrow logs and natural logs to help us determine how long it takes for an investment to grow to a certain goal, a certain final result. But today we're just going to preview this how long with a very non-mathematical but neat little estimating tool called the rule of 70, or some people call it the rule of 72. Which basically says the time it takes to double an investment is approximately 70 divided by the interest rate. Or if you like the rule of 72, it's 72 divided by the interest rate. Both of them get you pretty much to the same answer. Turns out that 72 is best when the interest rate is between 5% and 12%. Otherwise, we'll use 70. It also has to do with the number of compounds and whatnot. I'm not going to spend a lot of time on which is better. I just want you to be aware that if I wanted to know how long to double your money at, say, 8%, you could do that by, well, 8 is between 5 and 12, so let's use 72 divided by the 8%. It's going to take about 9 years to double your money at 8% interest. And again, that's just an estimate. It's not very mathematical. It's just kind of giving a preview to the mathematical way to answer that question, which we're going to see in tomorrow's lesson. As for today, we're going to look at exponential functions, solving exponential equations, sometimes by getting a common base, sometimes by using a logarithm. We're also going to look at logarithms and their properties and how we can solve log equations. Take a look at the homework, come to class tomorrow with questions, and I will see you then.